Hello everyone, welcome to this series of lectures on thermophysics and statistical mechanics. Through these lectures, I hope to give you a textbook understanding of statistical mechanics and its applications. The textbook I will be following is Concepts in Thermophysics by Stephen and Catherine Blundell. The reason for choosing this book is that it's an easy reading to follow, so if you are left with any queries, you can just check out the book. I'll assume that throughout these courses, you have the basic knowledge of understanding of high school mathematics. Alright, so let's get into it. I'll start off by brushing up two topics. These are taken from the first chapter of the book. Let's start with the definition of a mole. It means that the number of something as much as the number of atoms in 12 grams of carbon 12. It's an isotope of carbon. This may seem weird, but not so much when you consider that it is approximately the number of atoms in 1 gram of hydrogen. If the statement confuses you, consider the phrase a dozen eggs. It means the same as 12 eggs. If you had a mole of basketballs, you could create another planet Earth. A mole of atoms is equivalent to Avogadro number of atoms, which is a lot. So let's take a look at the thermodynamic limit. To understand the thermodynamic limit, let's take an analogy involving raindrops falling on the roof. Suppose we have a tiny roof. An occasional raindrop might fall and transfer its momentum to the roof with a certain impulse. If the area increases, the number of raindrops increases. So does the force experienced by the roof. But the amount of force per unit area seems to be the same for every case. Let's call this force per area as pressure. You can see that the average pressure is almost constant for any roof size. As the area increases, the fluctuations in the force exerted for each raindrop smoothens out, and this force looks to be much closer to the average value. We consider that as the area tends to infinity, the fluctuations to be almost non-existent. This is the analogy for the thermodynamic limit. Suppose we have a container of air. It has a certain pressure associated with it. If the container was small, we would have to worry about each and every molecule hitting the site to know the pressure and the fluctuation associated with it. That is the randomness of the molecules. In most cases, the system we assume is said to be in the thermodynamic limit. That is, the number of molecules in the container is so large that there is uniformity in striking the sides of the container. Thus, the fluctuations in pressure can be neglected and we can say that it is uniform. Thus, we begin with the statistical mechanics, which developed with the knowledge of existence of atoms. We start with microscopic states of a system and develop the macroscopic properties using statistical methods. The thermodynamic behavior of a system is asymptotically approximated by the results of statistical mechanics in the thermodynamic limit. That is, as the number of particles tends to infinity, the intensive qualities such as pressure and density they remain finite. Thank you and hope to see you in the next lecture.